We're going to look at another theorem that you can use to find limits. It's called the Sandwich Theorem, and the idea behind this theorem is very intuitive. We're going to suppose that you have one function sandwiched between two other functions. So here I got like a f of x and I got g of x, and then h of x is sandwiched between them. And so what that means here is that for all the values of x here, g of x is less than or equal to h of x is less than or equal to f of x. So h of x is between them. And in fact, this will actually work if this is true for all values in an open interval around C. So it doesn't matter what's going on around here. But in an open interval around C, if you got this inequality, then this will work. And the idea, sometimes they call this the squash theorem, because it's like h of x is squashed between these two. So the point here is if both f of x and g of x have the same limit as x approaches C, then h of x also has to have the same limit. Okay, so let me give you a quick example of how this works. So here we want to find the limit as x approaches 0 of x times sine of x. Okay, so technically we could do the product rule and take the limit of each piece. But let me show you how the squash theorem can be used. So what I'm going to do is I'm going to use the fact that that this x times sine of x is actually sandwiched here between the absolute value, the opposite of the absolute value of x, and the absolute value of x. So this is going to be sandwiched between these two because this is always going to be equal to negative x, this will be equal to positive x, and sine of x is always going to be between negative 1 and 1, right? And so if it's negative 1 and 1, that's as big as this is going to be, which is going to be equal to x, and any other value, it's going to be smaller than x, right? So this will be smaller than negative, or larger than negative x, bigger than x. So let me actually draw a picture here. So it's kind of like here's the absolute value of x, y equals the absolute value of x, and then here is y equal to the opposite of the absolute value of x. And I'm not going to necessarily do this right, but this thing is going to be like this. Okay, so this thing is going to oscillate up and down. Now, the amplitude is changing. It's getting bigger as x is increasing, but as the biggest it can be is going to be absolute value of x, and the smallest it could be is the absolute value of negative x. Okay, so this is actually sandwiched between these two. Okay, well, then what you notice is that the limit as x approaches 0 of the opposite of the absolute value of x, the limit here for this one is 0, and then the limit as x approaches 0 of just the absolute value of x, that's this one. So as you approach 0, it's going to be equal to 0. So x sine of x is sandwiched between these two functions, and both of them have the same limit of 0. So that means this will also have a limit of 0. Okay, so that's the idea. You're sandwiching the function between two other functions that you can find the limit of, and if both of those are the same, then the limit of the function sandwiched between them has to be the same as well. Okay, so now what I'm going to do is I'm going to use this theorem to prove a very special limit. Okay, and that limit is the limit as x goes to 0 of sine of x over x equals 1. Okay, so notice if you put in 0 in the denominator, you get a 0 in the denominator. So this is undefined, but there's really no way of simplifying this or crossing out the x so that you can actually plug things in. Okay, so there's nothing we know so far that could show me what this limit is, but as it turns out, these both the sine of x and x are kind of going to 0 at about the same rate, and so these kind of have the same behavior as you go to 0. So if you take the limit of sine of x over x, it actually equals 1. Okay. How can we show this? Well, we're going to use a geometric argument. This is such a neat proof. This is a really, really neat argument. So let's see if I can actually make this clear here. So first of all, just recall that if you have some triangle here, so here's a triangle, and this is the base, this is the height, then the area of the triangle is 1/2 base times height. That should be pretty clear, pretty familiar. You've probably seen that before. Well, the area of a sector here, kind of similar to the area of a triangle. So a sector is just this is a curve. This is part of a circle. So if you had a big circle and you had two radiuses coming out, and you took just that piece, so this is the radius, this is the radius, then this is a sector of that circle, kind of like a piece of pizza, right? And so the idea is this is kind of like a triangle. And so you would think that the area of this sector would be 1/2. This is like the base of the triangle. The radius is like the height of the triangle. So you would think it would be 1/2 base times height, and it actually is. It's just that the base here is the arc length s. Okay, the height of the triangle is r, and the base is that arc length. Well, if you remember, arc length is just the radius times the theta, okay, where theta is in radians. So arc length is r times theta. That's a well-known formula from pre-calc or unit circle trigonometry. And so plugging this into that s will give me 1/2 r squared times theta. So the area of this sector is 1/2 r squared times the radians, okay, of that angle. So now what we're going to do is we're going to construct a set of inequalities here, but we're going to use some geometry to do that. We're going to take, we got two triangles and a sector. So it says consider the following three areas. So one is the area of this triangle, OAB, okay. One is the area of this big triangle, OCD, okay, OCD, and then one is the area of this sector here, this sector, okay. So this is a unit circle, by the way. This is the unit circle in the first quadrant, right? And so this the area of this sector. So notice the area of that sector is actually trapped between the area of this triangle, this little triangle, and the area of that big triangle. Okay, so you could write that, you know, the area of this sector is between the area of these two triangles. So now let's see if we can come up with expressions for these three areas. Okay, so notice this is the unit circle. So this here is actually equal to the sine of x, and then this here is equal to the cosine x, right? And this radius is equal to 1. Okay, that's just regular unit circle trig. So the area of this triangle is 1/2 base times height. So the base is like the cosine, the height is the sine. Okay, so this is 1/2 cosine theta sine theta. Okay, so now what about the area of this triangle? Okay, well, notice here that this side is equal to 1, right? And you can think of this side as being the opposite, right? So if I had tangent of theta, it would be equal to the opposite over the adjacent, okay? But notice in this case, in this big triangle, that's a right triangle, and here's theta. Notice the adjacent side is equal to 1, right? And so what that would mean is tangent of theta is equal to the opposite over 1, right? So the tangent of theta is actually equal to the opposite side. So and so that means this opposite side is tangent of theta. Okay, that's actually what that's equal to. So tangent of theta over 1 is equal to the tangent of theta, which is to say that this side is the tangent of theta. So that's a little strange, but it would mean here that the area of this triangle here is 1/2 1/2, this is the base, right? 1/2, and the base is 1, and then this side is tangent theta. 1/2 base times height. And notice I could simplify this to just 1/2 tangent theta. Okay, now what about the sector here? Okay, well, the sector, this is the sector. Okay, the radius is just 1, right? And so if I use this formula, the area of this sector is 1/2 1 squared times the theta, right? And 1 squared is just equal to 1. So this could just be 1/2 theta. Okay, so these are formulas for these three areas, right? And the area of this sector is trapped between these two here. So what I could write here is, this is the smallest area, 1/2 cosine theta is less than or equal to 1/2 theta, and that's less than or equal to 1/2 tangent theta. Okay, so this is just saying the area of the sector is trapped between these two triangles. Oh, this should be cosine theta times sine theta. Sorry about that. It should be that. Okay, so now what I'd like to do is multiply everything through by theta. Okay, so what I'm doing then, this would be 1/2 cosine theta sine theta. So let me actually rewrite this out as it should be, and then I'll multiply everything through by theta. And then what I'm going to do is I'm going to rewrite this as 1/2 sine theta cosine theta. Okay, so what I'm going to do here is I'm going to, well, first of all, I can cancel out the 1/2s, and then I'm going to multiply everything through by theta. Okay, and if I do that, then what I'm going to get here is like cosine theta, and then I could rewrite, and then this would be the whole side divided by theta, but I could just then do just that divided by theta. And then this would just end up being 1, and this would end up being, I could rewrite so that 1/2 cancels out. I could rewrite this 1 cosine theta times sine theta over theta. Okay, so this is actually an inequality that I would get. And so what I want you to notice now is that this, just take this here, I could move the cosine to the other side, and what I would get is I would get that sine theta over theta, and this was the reason for doing this, because now I have the expression that I want to find the limit for. But what I would have is that this is less than or equal to 1 over cosine theta. Okay, so now I can do this piece here, and what I'm going to do is move the cosine to the other side, so that I get cosine theta is less than or equal to sine theta over theta. So what I get is these two inequalities here. Okay, and so now I could combine these two. So cosine is less than this, so I get cosine theta is less than or equal to sine theta over theta. Okay, and then sine theta over theta is less than 1 over cosine theta. And so what I get here, this is the sandwich here. I get sine theta over theta is trapped between these two. Okay, and so now that I get this, well, the limit as x goes to 0 of cosine theta is just 0. Okay, because that's, I'm sorry, it's just equal to 1. Sorry, is equal to 1. okay, because that's what cosine approach is. Similar here, the limit as x goes to 0 of 1 over cosine theta, that's also equal to 1, because you can take the limit of the top and bottom, that's going to 1. Okay, so in other words, sine theta over theta is, I've shown through this geometrical argument, it's trapped between two functions that are both going to 1 as x approaches 0. And so what it means is that this sine of theta over theta as x goes to 0 also has to approach 1. Okay? So that is such a neat theorem, and it gives us this very special limit that gets used in a lot of things. Okay? In particular, we're going to use it when we derive the limit, when we derive the derivatives or the instantaneous rate of change of the trig functions. Okay, this limit ends up getting used. So very, very important limit. This is kind of the argument that you would use to show that, and so that's really neat. And it uses the sandwich theorem with some geometry. So now what I want to do is just show you how you can use that limit now to find some other limits. So this is finding what's the limit as x goes to 0 of x over sine of x. It seems like, well, maybe the reciprocal of 1 is 1. So it seems like maybe the limit of the reciprocal would also equal the reciprocal of the limit or whatever. I'm not sure if that's always true, but one way to see that in this case it is true is I can rewrite this as 1 over sine x over x. And so in other words, if I inverted and multiplied, I would get that. And now I can take the limit of the top and the bottom, right? I could take, this would just be 1 over the limit as x goes to 0 of sine x over x. And you would see that that would go to 1, which is just 1, right? So this limit is also equal to 1. So the limit of sine x over x as x goes to 0 is 1, but x over the sine of x is also equal to 1. Either way, you're going to get 1. Okay? So now what about something like this? Okay? Well, this isn't the same as what we had before. It's not the same as sine x over x. And in fact, we got a 2x inside, which means that the wave is oscillating a little faster. So what you can do is you can rewrite this limit, limit as x here goes to 0. And I can put a 2 here, 2 sine of 2x, and put this over 2x. Okay, so in other words, the 2's would cancel out and give me this. Okay, but with this 2 there, or with that there, I can pull that constant multiple out, right? And I would get sine of 2x over 2x. Okay, now they're the same, so I could just let, for example, theta equal 2x, right? And then I would just get the limit. So as x goes to 0, theta is going to go to 0. So this thing could be rewritten as 2 times the limit of, as theta goes to 0, of sine theta over theta. Right? And this thing goes to 1. So this whole thing would go to 2. 2 times the limit is 2. So in other words, I can do this substitution as long as, as x goes to 0, theta is going to go to 0. So this will equal that. Okay? So basically, it's just like this is theta going to 0. Okay, so that's what that would equal. It would equal 2, not 1. So now let's try this again, or let's try this. This is a more complicated one. Here we got sine of 4x over sine of 5x. We want to know what this limit is. So what I'm going to do is I am going to multiply the top and bottom by the following. So first of all, I'm going to let's do this. I'm going to just multiply the top and bottom by theta. Okay, so I'm going to get the limit as sine of 4x over sine of 5x. And not by theta, but by x. So I'm going to multiply the top and bottom by x. An x here and an x here. Okay, so then what I can do is I can split these up. I can do the limit as x goes to theta. But I'm going to split them up like this. Sine of 4x over x. And this would be the limit as x goes to theta of x over sine of 5x. Okay, and so because basically I could split those apart like this, and then I could split the product up. So it would look like this here. Well, then I would have, I could rewrite this. I need a 4x down here, but then I can pull it out of here. So I'd get 4 limit as x goes to 0 of sine of 4x over 4x. And then this, and then I could do multiply top and bottom by 5, right? And then I'd be pulling out a 1/5. So I would have 1/5 the limit as x goes to 0 of, this would be 5x over sine of 5x. It would look like this. So, but basically, if you brought that back inside, it would cancel out and give you this. So I'm multiplying top and bottom by 5, but then I'm pulling out a 1/5, leaving the 5x up there. Okay, and then basically both of these are going to go to 1. Okay, just like these, like the original one and this one. So this is basically going to be 4 times 1, 1/5 times 1. That's basically 4/5. Right? So this actually equals 4/5. So that's kind of interesting. And then let me do one more. So what I'm going to do here is I'm going to rewrite tangent as sine over cosine. So this is the limit as x goes to 0 of, we could write this sine x over cosine x all over x. Okay, and so I could rewrite this limit as x goes to 0, and this could be rewritten as, this would be like sine of x times, I'll break it down, sine of x times 1 over cosine x, and this would be times 1 over x, right? You kind of got these three things. And then I could move that over to the sine of x. So limit as x goes to 0 of sine of x over x times 1 over cosine x. Okay, well this will just go to 1, and as x goes to 0, this goes to 1. So in other words, I can split this up. Limit as x goes to 0 of sine x over x, limit as x goes to 0 of 1 over cosine x. And there's no problem with this one because you don't get a 0 in the denominator. So you just get 1 here for that. And so those are some examples of how you can actually use that limit in different ways to find other limits. And in particular, when we find the derivative, that limit will be used to find the limit of the difference quotient involving trig functions. And so it is a very important limit when you're doing calculus.